Let's go. Okay. So first course on time series analysis. Maybe a little forward first. The purpose of this course is to provide an introduction to the mathematical, I insist, mathematical, and to a lesser extent algorithmic aspects of time series analysis. In this first course we will concentrate on what's called the time domain by opposition to the frequency domain, about which we will only say a few words in the final chapter of this course. And you would be seeing more about the frequency domain if there were a time series 2 course, but there is no time series 2 course because there is nobody available to teach that time series 2 course. The notes are, I hope, for the most part self-contained. Exact references shall be provided for the various unproved results, of which there will be quite a few. The course has been constructed by splinching the very classical book by Brockwell, which is the basis of most modern time series courses. And it's also mixed up with the book I told you about by Neusser and Shumway and Stuffer, which are a bit more recent. The structure of this course comes from the previous, from my predecessor, who until 2 years ago was teaching this course, who is Siegfried Hörmann, who used to be a professor at ULB, but has now gone to live in his home country of Austria, and he's abandoned us, so now I'm teaching this course here. But it's the basis of this course is his, which he taught for several years. I think I literally follow his framework quite precisely. So, in order to understand this course, readers are supposed to be familiar with the fundamental probability theory and mathematical statistics. You can probably follow a bit if you don't know anything about probability theory and mathematical statistics, but it will be not a very, it won't be as enjoyable, I suppose. Students at this course are also expected to have basic working knowledge of R software, because all numerical aspects of the course would be dealt with in this language. Functional R code will be provided throughout the text. Again, I insist, this is a rather theoretical mathematical course. It's in this respect a bit different from what you would get at other universities, where there's a question. Hello? I will cut your microphones. Hi. So it's a rather more mathematical approach to the theory. Other universities would have a more recipe-based course wherein you would cover more. You'd cover more topics, but probably less in depth. My intuition is that it's, at least at university level and in a university course for mathematically proficient students, it's more rewarding to delve a little deeper into the mathematics, less into the recipes, because the recipes you can always learn them by yourself. There's a lot of machine learning that's getting more and more fashionable about this. Last year I had one of the guys who's following the same course as you now, who did his master's thesis with me. He did the machine learning aspects and he did them all by himself like a big boy. He learned it through so he did his master thesis on this. He learned it through tutorials on the internet and on his own, and he made a wonderful master's thesis, which was awarded a 19 out of 20. He did a very, very good job, and basically none of the things he did we had studied together in the course, but they were all implementations of various algorithmic sophistications of the notions that we have seen together. I sincerely believe that if you understand correctly the theory behind the basics, you will then be very at ease for implementing the more black box approach that exists in the well, on an industrial level. So that's a very complicated way of justifying, a convoluted way of justifying my course, but that's the way I understand it. It's that I give you the understanding of the basics, and then, I mean, algorithmically anybody can do this. It's just, it's very, I mean, take in R or in whatever language you choose to use, it's very easy. You just press a button and then the computations are done. So that's not interesting, at least I find. So we'll be covering 7 main chapters. As I already said, I'm not at all satisfied with this chapter here, so I hope to be able to develop it a bit more, to make it more interesting for everybody. Maybe even go into some more algorithmic aspects. So the first chapter is an introduction with all the basic vocabulary. That's what we'll be doing today. Second chapter is very mathematical, but it will give us some kind of very handy tools for understanding the rest of the course. So for those of you who come from a maths background, it will be some things you already know. We'll be talking about Hilbert spaces and about the notion of orthogonality in Hilbert spaces. But so it will be rather easy for those of you who come from maths. For those of you who come from a less mathematical background, it might be a bit more hard to follow, but we'll try to make it enjoyable for everybody. You will need what we'll be doing here in the rest of the course. So don't think that because it's maths it's not useful. It is useful. It is useful for better understanding of the sequel. Third chapter would be a chapter on a family of time series processes called ARMA, which are the basic ingredients of the whole theory. And then we speak about forecasting, estimation, and estimation again. And that should basically be the 24 hours. Again, I hope that we will be able to do a bit more about this, but not sure. The exercises basically follow this structure. Okay? So, chapter 1, time series and stationary processes. Okay, the terminology time series is basically 2 objects. It's a collection of data and it's a mathematical model. It's a collection of data indexed in a certain set, obtained from repeated observation of the same phenomenon at different time points. For example, here we have the real gross domestic product of the US from 1930 to 2015. So here we see what it was valued at in 1930, 31, 32, 33, 34, 35, etc., etc., etc. So it's repeated observations of the same experiment over different time points. That's it. This, what I've plotted here, is a time series. This is a collection of data which is obtained in this way. Okay? But also mathematically, we would want to be able to describe this object and say what are its properties, what kind of, well, we do see that there is some kind of trend. What's the value of this trend? We see that there's a certain volatility around this trend. Can we describe this volatility? We see that there are certain perturbations in the trend. We see that something happened in this and here and here. We see that there seems to be a break here. Can we describe this model? Can we model this series in order to be able to describe the behavior of an entire collection of data that would behave in this way? Well, that's also called a time series. So a time series is also a mathematical model which describes data. So the collection of data is written little xt. These are the observations. And the mathematical model would be written capital XT, which is the random variables whose observation gives the little xt. Okay? In the vocabulary of elementary statistics, the data would be the observations and the model would be what's called the population. So the population is the fundamental principle that is guiding the creation of the observations. Each observation is then a realization of the corresponding random variable, and collectively the whole time series is a realization of the whole process xt. So we imagine that this value here, x1, is in fact the realization of capital X1 over, over the experiment of life going on. This value here, which would be x35, would be a realization of the 35th random variable over the history of the process. In this course, but really just out of simplicity, we will restrict to real valued variables, so we restrict to real value time series, but in principle we could also consider time series in more general spaces, like the Euclidean space in dimension D, or even in certain Hilbert spaces, or in functional spaces. The previous professor of this course was a specialist in functional time series, so in which the observations were functions. Okay. Usually the data are observed either in continuous time or in discrete time. So for example, here we have the data which is observed. It looks continuous, but that's just a fluke, because in fact it's we have observations at regular intervals like this, and then we've simply asked, well, R has decided to interpolate, so R interpolates like this, and he makes it looks like observations in continuous time. Okay, so typically we could either observe in continuous time, which is theoretically possible, but in practice it's not possible, or in discrete time. And in discrete time, you have to be careful that the observations could be made at equally spaced time points, and sometimes could also be made at non-equally spaced time points. And that becomes very annoying, because if you're observing something which happens in 1940, then in 1950, 51, 52, and then 1970, well, you cannot treat the data in the same way as if they were observed at equally spaced time points. Okay, so far?
Yes.
Okay.
Yeah.
So I'll go back to that's not so good. I would like to share my screen on R just for a while. Let's see if the technology wants me to. Where is my R? Here? No. Here. Does that work? Do you see my... What do you see? No, I'll quit R and start again, because some strange things are happening, so... Start again. Okay. Start again. Ouvrir le bac de partage. R-code, RStudio. Where are you? Here. Do you see my... What do you see?
No.
No. He doesn't want... Okay, and then I'll do something else. I'll share you my complete screen. That would be easier. There. Now you see... Now you see.
Yes.
Okay, so if you look in the slides, you see that below my graph here, there's some R code. Well, this is the R code, so I'll just show you quickly. For those of you who are familiar with R, you know this. So I've opened my RStudio application. Here is the file. So the top left window is the file with the different commands that I'm using. This is the console where all the computation is actually taking place. Top right would be all the different variables and data sets and everything that I've already created. And here you'll have all the packages and the help and the different available files and so on. So, for example, here I will choose the directory. So it's really a crash course on R for those of you who aren't familiar with this. So I set the correct working directory. I have my file, which I called here TS1, which contains the US GDP for the last since 1930. I create the years. I create the data, which is created by transforming my data into a time series. So TS actually transforms it into a time series data. So let's have a look. If I look at GDP US, it gives me simply a column of data, different data at different time points. And if I apply time series to this, well, he's now associated to this time series data, which he will then interpret as a time series with a beginning, an end, and a certain frequency. And then, well, I take the logarithm because it's high values, and because of the fact that it has high values, it has large swings. So we just take the logarithm to diminish the breadth of the swings of the data, and then I call this level GDPS, I forget why, and then I simply do a plot. And now we have a lovely plot, which you can see from 1930 to 2015. And then the whole point is, can we interpret this plot? Can we understand what happened here? Can we see a certain trend, and so on and so on and so on. So I see R as a giant calculator rather than anything else. Okay. So let's get back to the slides. So, just a few observations that can be made at this stage. First of all is that the data at hand covers only a part of the time series. So, for example, there was a GDP before 1930, and there was a GDP until 2020 in the United States, and probably there will be a GDP in 2021 and so on. So what we are observing covers just a part. The data cover just a part of the time series. Because there is in general, there is no natural starting or end point, we typically think of a time series as extending back into the infinite past and the infinite future. So we typically think of a time series of a collection of random variables or a collection of data indexed in time, but time goes from minus infinity to plus infinity. Okay? Second observation. The observations that we make are realizations of a random mechanism. This implies that we observe only one realization. The whole collection of data here is one realization of the experiment of the United States from 1930 to 2015. If we could turn back time and let run history again, we could obtain a second realization. But this is typically impossible. For example, with the GDP, it is impossible. And typically we are faced with just one realization on which to base our analysis. In statistics, you want many realizations. In statistics, you'd say that this is x1, this is x2, this is x3, x4, x5, and you treat all these as realizations of a same phenomenon. But that is not the case, because here, contrarily to statistics, these guys are not independent. They are each observations of a single experiment over a time. So in order to make some mathematics or statistics with this kind of data, we will have to make assumptions on the behavior of the random mechanism over time. We'll have to make assumptions on the general behavior as time moves on. I'll get the chat back. Okay. Third observation. Many time series exhibit non-random features. Non-random features. For example, here, that's what I was saying. Well, you see that there is some kind of trend. You see here that there is a linear trend in the evolution of the data. This feature is, so these non-random features of the time series are typical. And well, the first thing you have to do in order to analyze a time series is to get rid of them. So as you estimate the non-random part, and you analyze what's left. Because what's interesting, well, of course it's interesting to know the mean, but that's not the random part. The mean will just give you some information which you start by estimating, and then what's more interesting is what's happening in the noise around the mean. So that's what you want to look at. And then fourth observation, another feature that's often encountered in time series is seasonality. So the first one was trend, and seasonality or cyclicity is something that you also have to deal with. So for example, here we see, so what did I do here? So yeah, this figure 2 is the same as figure 1, but all I've done is I've said, well, let's imagine that figure 1 is a certain constant trend, mu t plus, let's say, another part which is more interesting, yt, which would be random. Well, then to go from figure 1 to figure 2, all I said is, well, instead of looking at xt, I look at xt minus 1. Xt minus 1 is what? Well, it's mu t minus mu t minus 1 plus yt minus 1. And if I just continue my computation, this guy kills with this guy, and I'm left with mu plus yt minus 1. So this would be the random part, and this is just constant. And if I look here, what do I see? Well, it seems that indeed I do have something like that. I do have a process which would be somewhere around, I'm guessing 1.9. No, I'm a bit low, I think. Somewhere around here. That would give us the mean. And then I have my observations, which give me the random noise around this mean. Okay, by taking first differences, I have gotten rid of the trend of my data. Okay, and then of course, once I've understood the random component, the random part in the yt's, well, in the difference of the yt's, I can then reverse engineer, and from here I can reverse engineer into understanding the behavior of xt's. Okay? So how do you do that? Well, it's very, very easy. In R, of course, the function that takes first differences is it's defined like this. When I was preparing my course, I realized that I had made a typo in my code. I think it's multiplied by 1,000 rather than multiplied by 100 in order to get this graph here. So that's how to get rid of the trend component. And as I was saying, there can be a cyclicity. So for example, this is a very famous data set which gives you the number of lynx trapped each year in the Mackenzie River. Between 1821 and 1934. Fascinating data set. And what you see is that there's a cycles of population, which it goes up and then it goes down and then it goes up and then it goes down and up and down and so on. And then there's larger cycles with larger peaks here, 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 and then there's smaller cycles with smaller peaks. And what you also see is that these cycles happen, but they're not at fixed length. Sometimes the peaks are separated by 8 to 9 years. Sometimes they're separated by a longer time. Well, that's something you'll have to learn to deal with, and so on. Yeah, something I didn't say is that there's lots and lots and lots of resources available on the internet. For example, here you can click, I think you can click in the PDF and you will be led to a site where this guy has done lots of analysis of time series data. Another example of time series which exhibits seasonality and no trend really, at least no general trend, would be the monthly sales of new family houses in between 1973 and 1995. We see that there is strong seasonality within each year. So between 1975 and 1976, 78, 79. So like this, we see that there's strong seasonality within each year, and so on. We also see that there is there are cycles of over the different years. So there seems to be a cycle here, and then another cycle, downward cycle here, and then another upward cycle here, and then a downward cycle here, and then an upward cycle here, and so on and so on and so on. These non-random parts will have to be dealt with. They'll have to be eliminated because their presence actually pollutes the understanding of the random component that is left when you've gotten rid of all the non-random components of your model. I think this is it's one of the last examples I'll give you. So this is half-hourly electricity demand in England and Wales from the 5th of June 2000 to the 27th of August 2000. And you see that you have two types of seasonality, a daily pattern and a weekly pattern. So daily and then a weekly. And if we collected data over a few decades, we'd probably see an increasing trend. And we'd also see some longer cyclic patterns, probably in relation with the economic situation in the country. So there's more examples. So here I give you the example of the Swiss market index. This data set is actually quite interesting because you see a few things. So it's the Swiss market index plotted against time. This is the raw data on a logarithmic scale, and you see different things. So you see the internet bubble, you see the financial crisis. We'd probably see the election of Trump somewhere in here, but I won't be getting political in any way, so I'm not going to talk about Trump. So what's probably more, so this here is, I mean, it's interesting, but it doesn't tell you anything you don't really know, except that there was a crisis at certain times. What's interesting is you look at the second panel, so if you look at this panel here, and so this is what it's the return on the index plotted, so it's the return on the index, so the percent, so you look at the difference between so you look at the rate of increase or decrease of the index, and here what we see is that you have, so you've gotten rid of the trends, but you see that when there's a crisis, there's a lot of increase in the volatility. Here as well, there's a huge increase in the volatility. Well, that's something that's also can and needs to be analyzed. It's called volatility clustering. And it's also something which is typical of financial market data. And if you like that kind of stuff, well, feel free to play around with it. So there's lots of data sets available in R. So for example, if you use the code which I give you here, you get lots and lots and lots of different data sets. So for example, you have the sunspots data sets, you have the Johnson & Johnson, you have the speech recognition, you have global temperatures, you have New York Stock Exchange, and you have, what is this? I forget what it was. It's called recruitment, so I guess it's something to do with recruitment, but I can't remember what it was. Okay? So, before we take what's a well-deserved break for me, and probably an unnecessary break for you, let's conclude this introduction by talking a little bit about what makes time series analysis different from classical statistics. Something we've already said is that time series points are dependent and correlated, whereas in statistics, usually independence between the observations is assumed. In truth, what you want to model in a time series analysis is not the data points, it's the entire sequence of observations. That's what's interesting. What's interesting is the evolution of this sequence of observations. So not the individual data points, but the entire sequence. Roughly speaking, in statistics, the experimenter can repeat the experiment under the same conditions independently. In time series, we cannot redo the experiment. We're stuck with what we have, and we only observe from a running process. Thus, we are confronted with a situation where there is in principle just one observation. We cannot turn back the clock and get additional trajectories. The situation is in fact even worse, as we typically observe only the realizations in a particular time window. So for example, here we only observe from 1880 to 2000. Well, that's quite large, but still. Here it's only from 1960 to 1980. In order to make a meaningful statistical analysis, we will need to make many assumptions on the data. And one of them is that the observed part of the trajectory is typical for the whole time series. So what we observe actually teaches us something about what we need to understand. So this idea is related to a concept that we'll be studying today, which is called stationarity. This makes the fact that we need more complex models to be able to say anything smart. But on the other hand, this dependence will also be crucial for the forecasting. And forecasting is basically what we want to do. When we have a time series, what we want to know is where is it going to go? What's going to happen in the sequel? Can we make a nice prediction? I will give you an example of a very nice data set, which I will not be discussing mathematically, but which I will leave you with. Nope, that's not my data set. This is my data set. So for example, this is an interesting data set because we have the popularity of Donald Trump on Nate Silver's webpage. I don't know if you know of Nate Silver's webpage. If you don't, well, voila, enjoy. Go and have a look at this. And here we see evolution in time of the popularity of Donald Trump. This is a time series. And what we can see is that he's, well, basically more and more popular as the election nears, which is probably very good news. So, no politics. Okay, is this comfortable for everybody? Are you happy with the way the course is happening so far?
Yes.
Okay.
Yeah, 100%.
Yes.
Okay, so that's for you to get depressed with. Let's have a break. I'm exhausted. We have a break. I'll shut the video. I'll shut the taping. I'll try to make a few videos for one course because they get very heavy. As you can see, we're nearly at 1 gigabyte of